And so yesterday we finished talking about the different kinds of defects. So today I want to talk about how can we know what defects are there. Well, one of the best ways is by looking at the material. We know that just by looking at the material, usually, unless the defect is very, very big, we can't see the defect, right? Our eyes are not able to resolve things that are on the micron scale or even less than submillimeter. So I want to talk a little bit about how we can actually see the defects. And that's by using microscopy. Okay, so usually when we look at a piece of material, it just looks smooth to us, like if the glass on your tablet or your phone usually looks very, very smooth to your naked eye. The table here looks very smooth. The metal on the side of the table looks really smooth, but we know that there are lots and lots of defects in there. They're both, they have volumetric, planar, linear, and also point defects. So how do we study what is there and how many of them are there? We can use light, but by using light, right now we can observe this with light, but it's not telling us a lot of information. So there are a couple of different ways. One is we need to prepare the material surface so that we could get the information we want. And that is done by polishing first and then etching. Okay, so why do we need to polish the surface of a material that we want to look at? We're trying to make it as flat as possible. Why do you think that might be important, to make a surface as flat as possible? Yes. Yes, so the light can reflect, but what about using light to look at a surface that will be helpful if it's not very, high at one point, low on another point, and then high somewhere else? Why would we want it as flat as possible? You've all used optical microscopes before, yes? At some point, or even with your camera. If you're trying to get a picture of somebody who's standing very close to you, and also get as much information as you can with something in the background. So let's say you're trying to take a picture of this board, and you want to have a very clear picture of everything that's written on the board. And you also really like me, so you also want a picture of me inside. You want me in the picture with the board. Is it easier for you to get that information, to have a clear picture of my face, if I'm standing very close to the board, or if I'm standing very close to you? Close to the board, right? Why is that? Why would it be difficult for you to get a good picture of me and the board if I were standing very close to you, but the board is very far behind me? Like, what would happen to that picture? Yes?
You will be blocking most of our views.
Okay, I will be blocking your view, that's true. But what else? Yes, the black background will be blurry. So either you get a really clear picture of my face and the background is blurry, or you get a really clear picture of the background, but my face is blurry, right? Okay, you've all had that experience taking pictures. It's the same thing with the optical microscope. It's called the depth of focus. It's hard to get a good focus if you have different depth of focus for the light. And that's why you want to get it as flat as possible so that you could get the clearest, most focused picture for the entire sample that you have, instead of just one point on the sample. So that's why we polish first, get it as flat as possible so you get the widest area with the same depth of focus. And then so when I was an undergraduate student, I worked for a professor. I worked for his graduate student. And I had to do a lot of polishing. It's very, very boring. You basically hold a sample, and you put it on different kinds of sandpaper, and then you use different kind of grit to, there's a rotating wheel, and you hold it. And back then, a long time ago, we didn't have automated systems of holding the sample in place. So I personally had to hold the sample in place and just sit there and make sure I didn't tilt the sample that is flat and do it for hours and hours and hours. And that's why the graduate student didn't want to do it, and they hired me to do it. So very, very boring. And then after you are done making the sample as perfectly smooth and flat as possible, do you know what they did with it? They took a chemical etchant and etched it to make it not smooth. Okay? It's very annoying. But do you know why they have to do that? So etching is to use, most of the time they use chemicals to remove parts of the material. And this is required because in order to get information out of that very flat sample, if you just had a very flat sample, the light, so let's say you have a sample like this and you have grains underneath it. And let's say this is a direction pointed this way. You have different planar directions. This is a different phase altogether. Okay, something like that. And if you were to shine and you polished it very, very flat, and you were to shine a light on it, it would just look like a smooth surface to you. All the light that's reflected would just be bounced back because it's so smooth, and you wouldn't get any information out of it. And so that's why you have to, after you take the time to make it very flat, you have to actually roughen the surface. So you use a chemical etchant. And the chemical etchant will remove part of the surface, but it will remove it in different amounts depending on the energy of the atoms that it's encountering. So if an atom is already not in the most stable position, so if it's already not sitting in the lowest energy state possible, it's sitting slightly higher energy, it is more likely to react with the etchant and more likely to be removed. So it will remove parts of the material, and the parts are those with higher energy state. And so it kind of depends on, so we know grain boundaries where the different crystals meet, they have higher energies, right? So remove those. So maybe this area will be removed a little bit more. And maybe this phase reacts with a chemical a little differently, so it has a lot of materials removed. Maybe this one has just a little bit of materials removed. And because of the direction of the planes, the atoms here happen to have higher energy than the atoms here, so it'll have a different amount of materials removed. Okay, so it's going to remove material from the surface in different ways depending on the energy of those atoms on the surface. So if it's sitting at a high energy area, it's going to be removed more easily than if it's sitting in a low energy area. It's more stable if it's at a lower energy. Okay, so you end up with this very, very fine, rough surface that will reflect light differently. Right? The smoother the surface, the more it will be reflected in one direction. The rougher the surface, the more likely that the reflected light will be scattered. Okay, that makes sense? I know it rains a lot in Taiwan. I'm from California, it never rains. Maybe it rains 2 days a year. So no one goes outside when it rains because it's scary. But here, you know that when you're on the road, right, and if you're driving at night on your scooter, if you're driving at night and you have your headlight, and I don't know if you ever noticed this, but during a drive time, you will see your headlight reflected off of the road in front of you. You can see your light beam in front of you, right? Because the reason why you can see it is because that light hitting in the road and reflecting back to your eyes, so you can see it. On a wet day, after it's been raining, you will not be able to see your headlight as well. Have you ever noticed that? It does, like if you look the next time it rains and you're at night driving, look at your headlight in front of you on a wet road. You're going to think like, wait, is my headlight on? Like it might seem like your headlights are not on because you don't see the light beam in front of you. Has anyone ever noticed that? Maybe it happens so often here that you just don't notice, but I've noticed that. And the reason why it looks like that is because when it rains, the water forms a very smooth surface, and the light just shines from your headlight and goes forward in the same direction, right? In the reflected direction. But in a dry road, the road is very rough, so a large part of that light is going to bounce back, be scattered back towards your eyes. Okay, so the same thing is happening here. If it's very flat, it will have a similar angle of incidence to this angle of reflection. But if it's rough, then it's going to become scattered. And what does that look like to your eyes under a microscope? Is that you're going to see dark and light parts. So if you're looking at under a microscope, this is your specimen, and maybe these are your grains, something like that. One, you're going to see the grain boundaries. Those are going to appear dark to you because those are very rough and they scatter the light. So the light is not bouncing from the microscope back to your eyes, it's scattering it. So it looks dark. And then the different grains, some of it may look darker and some of it may look lighter, okay? Depending on how rough they are, that surface. And the roughness depends on the energy of the atoms at the surface. And so by polishing and then etching it and looking at it with light, magnifying the surface, you will be able to see grains, actually see the grains of a material. And be able to see, does this material have large grains or small grains? Does it have a lot of defects? But light has when we talked about X-rays, we talked about how we needed to use X-rays to look at material structure because X-rays have the similar wavelength to the size of the atoms that we're looking at, the unit cells, right? And so we know that by using just visible light, we have some limitations to how much we can see. The visible light, the shortest wavelength is going to be bigger or equal to about 400 nanometers. And so it would be really, really difficult to see anything lower than 400 nanometers because the light waves are just the wavelength is too big to interact meaningfully with the material structure. So if you wanted to look at things even smaller than, say, half a micron, then you need to use electron microscopy. Okay. So instead of using a beam of light, shining a beam of light at your material surface, you're using a beam of electrons. Okay. So just to review, we know that the energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength of the light. This actually also applies to everything else, including you. So everything has a wave-particle duality. Okay, you can take any particle and calculate its wave properties or its characteristics as a wave, and so forth, okay? All right, so if you increase the velocity of an electron, so that would increase its energy, right? So if you were to increase the energy, what will happen to your wavelength? Will it go up or down? If E goes up, lambda goes down, because this is a constant, right? Okay. So if we increase the velocity or energy of our electrons, we can actually get electrons to behave as a wave with very small wavelength. And you can get the wavelength of an electron to be around 0.003 nanometers. A typical atom is around 0.1 nanometers. And so you could get really good resolution, atomic level resolution. You could see individual atoms with electrons. So I mentioned that. So electron, usually you think of as a particle. It can behave like a wave, so we could use it just like a beam of light in that same way. This desk also has a wave-like property to it. I have a wave-like property to it. But our energy is so big, right? Like if you look at my mass and how, I don't run very fast, but if I were running, I would have some energy associated with my mass and my speed. That would be the E. And my wavelength would be really, 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 really small. And you could calculate for yourself, you know how much you weigh, how fast you could run. You could calculate the wave-like property of yourself, and you will see that it is so short, the wavelength, your own wavelength, is so short as not to be detectable. We don't have any instruments that are good enough to detect the wave-like nature of ourselves. And so that's why usually for large objects, you don't see them behaving as waves. It's not because they don't have any wave-like properties, it's just their wavelengths are so small that it's not detectable. Okay, but electrons are very light, and so we can detect the wave-like properties of electrons. And we use that in microscopy. So there's several different kinds of electron microscopy. You have transmission. Okay. So basically, this is when the electrons go through the specimen. So you need to have very, very thin specimen so that the electrons don't all get absorbed, that it can actually go through. And you can study things like, you can see dislocations in a material. You can use it to study viruses, very small biological materials. But the problem is that the samples have to be very, very thin. And so it's not always easy to prepare a material like that, to be thin enough to be used in TEM. And you can look at both the transmitted light, but also the diffracted light from these materials. And they're very complicated ways of studying the TEM images. And I'm not going to go into it here. If you do end up studying material science, and go to graduate school, you may end up taking an entire class just based on how the TEM works and how to look at the results, how to analyze the results of a TEM. But it's a very, very powerful instrument and very powerful tool for studying materials. And then you have SEM. S stands for scanning. So this one you're looking at, so this obviously is looking at transmitted electrons. This one you're looking at reflected electrons. So electrons that reflect off the surface. Again, you can see very small features down to atomic size. The issue about preparing electron microscopy in SEM is that your material needs to be at least somewhat conductive, because the electron needs to hit the surface and scatter or reflect. And if your material is not conductive, it will likely absorb the electron. So you can get energy that is absorbed by the material, and the material can heat up, and then you can end up ruining your sample and not getting a lot of detail. So a lot of times, if you're looking at materials that are not conductive, you actually have to coat it with a very thin layer of conductive material so that it conducts on the surface. And so that's a preparation issue. By coating something with another material, you're losing some resolution, right? You're going to lose some of the resolution that you would have had without the coating. A lot of times you also have to do this in high vacuum. So if you're studying biological materials, they may not survive in high vacuum. And also if you're wanting to study materials that are alive as opposed to after they die. So if you're looking at how a cell is functioning and you want to watch it as it's still alive, then it's difficult to do it with some of these methods. There've been work on very, very innovative work that have been done so that they can have special environments where these samples can live in and be able to study it with TEM and SEM. So definitely it's possible, it's just more complicated and expensive. And then the last kind of microscopy is called the scanning probe microscopy. The AFM is probably the most widely known of this kind of microscopy. Has anyone heard of the AFM? So it's called atomic force microscopy. And the way it works, instead of using light, is actually using a probe. So something, a little stick. So this is my surface of a material that I want to look at. If I can make a probe, a little stick that can go on the surface and follow the surface along and go up when the material goes up, go down when the material goes down like that, then I could kind of trace that surface, right? But in order to do that for a material, if we're looking at, nanometer range, then the tip of my material, that probe, will also need to be nanometer size. And that's exactly what people have made. They made what is called they make something like this. This is an arm with a tip on the end, and the tip is made very, very sharp, so that the very point is only maybe like 10 atoms big. It's very, very sharp. So it's on the order of angstrom, well, usually nanometers, that tip. Okay? And then what they do is they shine a laser to the surface. They follow the surface of this probe, and that laser is reflected to some light collector. And as the probe goes along the surface, it's going to tilt. That surface of the probe is going to tilt depending on the contours of this material, right? And so the reflected laser will change direction depending on what the material surface looks like. And so by looking at the collected laser beam, it knows the contours, the topography of that material surface. So that's called the atomic force microscope. Something that's very interesting about the atomic force microscope is that not only can it look at the surface, what they can do is that they could functionalize the tip of that probe. They can make it magnetic. They can make it to interact in different ways with the material. So you can now, instead of just looking at the surface, you could do that with the tip, but you can also detect areas of different properties, like magnetic properties, for example. Because if your tip is magnetic and your material is also magnetic, they're going to interact with that tip differently than if the surface is not magnetic. So it can actually find small traces of magnetic portions of your surface and map it out. So basically, if you have a surface like this, the tip just rasters back and forth, across your material, and then you collect the laser light that comes out, then you could plot what that surface looks like. And so you could functionalize the tip and get additional information out of that microscopy. So those are the basic types of microscopy that we use to study the structure and the defects of materials. You use optical, electron, and probe. So now I want to talk about diffusion. We talked yesterday about how when we're looking at vacancies, and the equations that we have only tell us the thermodynamically stable state of our material. So what will happen if you give the material an infinite amount of time and energy, how will that material behave, right? But we know that that's not practical. In real life, we don't have an infinite amount of time and energy for any given system. We need to know the rate of the system and how that depends on temperature and other types of energy constraints. And so we talk about diffusion. So let's say you have a piece of iron. So here is x equals 0. So this is the surface of your iron bar, indefinite in length. And you want to add carbon into iron because you want to make steel. Okay. So you have a carbon gas in the front, on the surface, to try to get the carbon to go into the iron. So you could plot, this is x, this is concentration of carbon. And whatever is at the surface is the maximum. And then the amount of diffusion that goes in will look something like this. There might be a lot of carbon right at the surface, but as you go into that bar of material, it's going to become less and less. And we have different kinds of diffusion. You have an atom missing here. What is that called in terms of defects? Vacancy, right? This is a, what kind of defect? In between the interstitial, right. Okay, so you have vacancies, interstitials here. And if you have self-diffusion, that is when the atom inside the material moves. So it's not a foreign atom, it's not an impurity, it's just the atom will move to an empty spot. If this atom moves here, then the vacancy moves this way, right? So vacancy diffusion and self-diffusion, same thing, just in different directions. Okay, and you can have, so you have different kinds of diffusion, vacancy diffusion, interstitial diffusion. So if this interstitial atom moves to a different place. And then you can also have what is called interdiffusion, is if you have a substitution defect that moves. So that would be an interdiffusion. Self-diffusion, the atom of the same kind. Vacancy is when vacancies move. Interstitial is when interstitials move. Interdiffusion is when substitutional atoms move. So just looking at this diagram, we know that it takes a certain amount of energy for any atom to move, right? So which one would have the lowest, would you expect to have the lowest activation energy for diffusion? Which one of these four kinds? What is it?
Interstitial.
Very good. So interstitial has probably, most likely, the lowest activation energy because it has the most spaces to move, right? Just like I see lots of people driving scooters. Much easier to move on the streets than cars, right? Because you could go in between cars and there's lots of space. So interstitials have a low activation energy compared to, what do you think would be the next one? Between interdiffusion vacancy or self-diffusion, which one might have the less? So thinking back to microscopy, when we're talking about etching and removing atoms, right? That's causing atoms to move. What kind of conditions creates an area where atoms are more likely to move? Areas of high energy or low energy? High, okay. So which one has higher areas of energy? Is it substitutional or self? Substitutional, right. So the activation energy for a substitutional atom to move, it's greater than interstitial, but it's going to be less than a self-diffusion. Okay. And the self-diffusion is going to be similar to the vacancy, because the vacancy can't move unless another atom moves. Okay, so where can we get this energy to overcome the activation energy for diffusion? So we know we want to diffuse carbon into iron to make steel. Where might we, and then we know that depends on if the carbon is interstitial or substitutional. It has different amount of activation energy in order to go into this bar of iron. But where would we get that energy from? Most likely. If you were to try to get carbon into iron, how would you make sure that you have enough energy to get the carbon to move into the iron? Yep, you heat it up, right? So you add temperature into this process. So let's look at the equations that describe this process. So dC/dt. Okay, C equals concentration of whatever you're trying to move, to diffuse. T is time. x is distance of diffusion. And you can always use this equation, second differential, to make things a little easier, because a lot of times we're using something like this. You have a bulk material, you have some surface concentration of materials you want to add. People have come up with a slightly less easier to solve equation for concentration and diffusion. So I'll tell you the conditions first. So at T equals 0, the concentration C of 0 is the same across the entire material. So another way to say this is that at T equals 0, C equals C0 at, so that's condition 1. Condition 2 is that you have a constant surface concentration, CS. So the surface concentration is constant, it doesn't change. And then the third one is that at T greater than 0, C equals C0 at x approaching to infinity. So I'll show you schematically what this means. You have a bar of iron, and you have some initial concentration of carbon within the material. So maybe you have a few carbon in there just from impurities, it already exists. And then you have a surface concentration of carbon that's constant. Okay? So what that will look like is this CS, and you have some C0. And the concentration, as time goes on, will always go to C0. So that means that this bar is very long. You never reach the end of that bar in terms of your diffusion. So at T1, it'll look like this. If you give it more time, it might look something like this. So this is T2. So T2 is greater than T1. Still, your surface concentration doesn't change. It always starts at CS. It always ends up at C0. But in between, your concentration will change. Okay, and then if you give it even more time, still start at CS, something like that. So if you can satisfy all of these conditions, which is not that difficult, then you can take that differential equation and write it like this. Okay, you can use this equation to describe diffusion. So Cx is at some distance what your concentration will be. C0 is your initial concentration. Cs is your surface concentration. X is distance. We already wrote that down. The only thing you don't know here is D, and that's a diffusion coefficient. And you might not be familiar with the error function, ERF. It's called the error function. It's just a mathematical function. Just like a sine or a tangent, right? Those are math functions. You stick one number into the function, you apply the function, you get a different number out. Error function is based on probability calculations, but it's not really important for what we're doing here. You just need to know that it's a math function. All right, so how do we use this? Oh, before I go there, this equation tells us how diffusion will change depending on the distance that it has to diffuse, right? It tells us how things will change based on the time that you give it to diffuse. It tells us how things will change depending on the surface concentration. But it doesn't tell us anything about temperature, right? Nowhere in this equation do we see T, temperature, okay? But we know we need energy to have diffusion. So where does this energy come from? It goes into the diffusion coefficient. D0 is some constant. Q of D is activation energy for diffusion. R equals gas constant. And T is temperature. Do you recognize this equation? Does it look familiar to you? The Arrhenius equation, very good. Where have you seen this before in this class? When we were talking about what? Vacancies, right? We were looking at number of vacancies, and it depended on the activation energy for creating a vacancy divided by temperature. Exact same form. Okay, so again, the Arrhenius equation is essentially what you will use anytime you are looking at how temperature affects rate, how fast things move. So you use the Arrhenius equation anytime you're looking at how temperature affects the rate of something happening. So here, temperature affects how fast diffusion can occur. Okay, that's where our energy comes from. And so, just like with when we talked about vacancies, if you take the natural log of that equation, you get the equation of a line. And you plot this line. The y-intercept will be the natural log of d sub 0. You get a straight line with the slope. That's the negative qd over r. So you could calculate or measure the diffusion constant, d sub 0, and the activation energy for diffusion of lots of materials by doing experiments. You can use a fluorescent tag so that you can actually visually see how many carbons you're getting into your iron, right? You could set it as different temperatures and then measure how much your carbon is going into your iron. Plot this line and be able to measure the d sub 0 and the diffusion, the activation energy for diffusion. Okay, and in fact, this is what people have done for many, many different material systems. This is how they find out what the activation energy is. So you could look in a book online in a database for the activation energy of carbon into iron, for aluminum into silicon, for lots of different things. And you might wonder, how do they know this? How do they know what the activation energy is by doing these experiments? So I want to give you a practice problem. Calculate D, the diffusion coefficient of carbon into iron, if you're given a system where the surface concentration of carbon is 1.0. The initial concentration of carbon inside this iron bar is 0.2 weight percent. And at some distance, you have 0.35 weight percent carbon. And that is at 4 times 10 to the negative 3 meters after 1 hour. So this is the information you're given. You're being asked to calculate for D. So what equation would you use? You have two equations, right? You have this one with the D, that one with the D. Which one would you use? That one, yeah, because you have the information. So go ahead, start working on it. Actually, let me go through it with you a little bit because you probably are not familiar with working with error functions. So, okay, all right, so you have this C 0.35 minus 0.2, 1 minus 0.2, and that's equal to 1 minus error function of x over 2 square root of dt. And let's use z as what's inside the error function. So if we solve for this part, we know that the error function of z equals 0.8125. Any questions so far about how I got that? So I just calculated this, moved the 1 over, got rid of the negative. So far, so good? I'm just representing the z. I could have written out the x over 2 dt. It's just making it easier to write. Does anyone's calculator have an error function on it? Mine doesn't. Okay, so if you don't have an error function, if you have an error function on your calculator, great. You could just plug it in. If you don't, then you have to do what I did, which is look up the error function table online. So if you have your smartphone or a tablet or something, you could go ahead and do that right now. Look up the error function table. If this is an exam, I would provide you with the error function table. You won't have to look it up. But basically, what you will find is something like this. It's a table with z, an error function of z with different values. And you're going to see lots of values, but you're going to see this. For those of you who were able to look up the error function table, do you see this in the table somewhere? Those numbers. Lots of other numbers as well. It goes from z from 0 to some other number by increments of 0.5. So it's like 0.05, 0.1, 0.15, 0.2. So you're going to see this. All right. When you see something like this, then you can use that table to calculate for z. So we know that the error function of z, what we have is 0.8125. So it's in between these two numbers. So our z would be in between these two numbers. And then we take the difference between the two smaller numbers and divide it by the difference between the two larger numbers. So what we're doing is z minus 0.90, 0.95 minus 0.90 is equal to 0.8125 minus 0.7970 divided by 0.8209 minus 0.7970. And then if you do the math, you'll find out that z is equal to, anyone calculate that? What did you get for z? Anyone have a number? Yes. Does this kind of make sense to you in terms of where error function z sits and where z? It's between these two numbers, so z must be between 0.9 and 0.95. It is closer to the bigger number, and so z must also be closer to the bigger number, right? If on a test you run out of time and you don't have time to do this, it's not that hard, but if you don't have time to do this calculation, you can absolutely just eyeball it and say z will be between 0.9 and 0.95. It's a little more than halfway. So I'm going to say 0.93. Good enough. If it looks like it's right in the middle, 0.925. You can absolutely do that on the test and just explain, write it down, running out of time, just estimating z. That's fine. Okay. This class is not an arithmetic class. So as long as you understand the concepts, I'm not trying to catch you on a mathematical error here. Okay. All right, so z is this. So now we know this equals 0.9324. So we calculate for d, because that's what we're looking for. So x is 4 times 10 to the... d is usually represented in meters squared per second, so I'm going to convert my time into seconds. So 1 hour is 3,600 seconds. So please calculate for d. Does anyone get a value? You're solving for this equation right here, right? What is it? 1.27. times -9 meters squared per second. Did anyone get something different? Everybody got the same? I got a slightly different number. I'll go with yours unless somebody has something different. Did you get something different? You look like you. What number did you get?
2.0449.
Ooh.
2.0449. And I don't know why it's E minus 8.
-8? 2.0 to -8. I got 2.6 times 10 to the -11. So we all need to check our math. I need to check mine too. But it's one of these. You would square both sides, right? Okay. You move D over to this side, that's over. So D equals, do we get a fourth number?
I think it should be 1.28 times 10 to the -9.
All right. Perfect. Okay. All right, so that's the diffusion coefficient for carbon into iron at that particular system, okay? Now, I have another question for you. If we increase the time for diffusion, so instead of 1 hour, I say I want to go to 2 hours. If I increase the time, what will happen to my diffusion coefficient? Will it go up or down? Okay, I have a vote for going down. I see somebody else, you in the back, you think it won't change, right? Okay, anyone think it'll go up? So we look at the equation. D should stay the same, because D is not dependent on time, right? Diffusion coefficient is only dependent on the activation energy and the temperature, the energy you give it. All right, so now, if I have the same thing, I have the same system. Oh, let me ask you another question. So let's assume this is substitutional diffusion. Okay, I tell you that this structure, carbon is going into iron substitutionally. But I'm going to give you a different piece of iron with a different structure, where carbon can go into it interstitially. What will happen to my D, diffusion coefficient? Will my D go up or go down if now I'm diffusing carbon interstitially? We know D is dependent on Q or T, right? We're not changing the temperature, so T stays the same. Will Q change whether it's substitution versus interstitial diffusion? Do you expect the activation energy to be different? Yes. Which one will be higher? Substitution or interstitial? Which activation energy? What will use more energy to move? An interstitial carbon or a substitution carbon? Substitution carbon will take more energy, right? So the activation energy for substitution diffusion will be higher than for interstitial diffusion. So by making it interstitial, our Q goes down, right? We have lowered our activation energy. Would you then expect the diffusion coefficient to go up or to go down? Okay. So we have a little bit of time to give you another problem to do on your own, and then we could check with each other. So let's say we have the same system. You work at a factory. You're trying to get carbon into iron to make a certain kind of steel. And you know this is your system. And you know the diffusion coefficient because you calculated it. And you're being asked to produce a material. So you want C of x, T, to be equal to 0.4 weight percent at x equals 4 times 10 to the negative 3 meters, and T equals 1 hour. So everything stays the same except you want more carbon, right? You have the same x, you have the same T, you have the same surface concentration. But instead of and you have the same initial concentration of carbon. Everything stays the same. But instead of 0.35 weight percent carbon at 4 times 10 to the negative 3 meters, you want 0.4 weight percent carbon. So you work at this factory. You've been asked to produce this steel with a different carbon percentage. What can you do to make that change if I'm telling you that this has to stay the same? So you have to get it into the same distance into the material, and that you only have your furnace for 1 hour to do this, so you can't lengthen the time. You can't heat it up for a longer time. You're the engineer. You have to produce this steel. What would you do? What can you change to make this happen? So these two must stay the same. The C sub 0 is the same because you're starting with the same piece of iron. But you could change other things. So what could you change to increase the amount of carbon? So one option is you can increase or decrease the temperature. You can increase the temperature. Is there another option? You can increase the surface concentration. You could put more carbon on the surface, right? So let's see which one is easier. So do the calculation for both. And you may need some additional information in order to calculate for T. So you can work with your neighbors and let me know what you find for either scenario. If we just increase temperature, what will we need to increase the temperature to? What is the new temperature we need? And if we just increase surface concentration, what will the new surface concentration have to be in order to get this condition? I would say, like, computationally, this is the easiest. So did anyone find the answer for this yet? Because for this, you've already done the calculation for most of it, right? Your x is not changing, your d is not changing, your t is not changing. So this should be an easy calculation. Did anyone calculate for CS? The new CS? Surface concentration. So we plug everything in. Z hasn't changed, right? So ERFZ 0.8125. Calculated that before. So you plug this number into here, calculate, and CS equals, okay? So you can adjust your surface concentration of carbon up to 1.27 weight percent carbon. Then you would get 0.4 weight percent carbon at 1 millimeter into the iron after 1 hour without changing anything else. Let's say you cannot adjust your surface concentration and you have to adjust the temperature. Then your calculation becomes more difficult, but you should still be able to do it. So is anyone stuck with their calculation or feel like you need more information? I can't actually give you the right number because I used the wrong number from my previous calculation, but I could show you how to do it. But did anyone get a number yet? You need D0. Okay. So we have these two equations, yes? And for increasing, the T would mean that we hold the surface concentration constant. So we have 0.4 minus 0.2, 1.0 minus 0.2 equals 1 minus error function of z. So you will have to find a new number for z. It will be different, right, from before. But I'll let you do that. But I'll show you how you can find this. So if I take the natural log of both sides, so far so good? Does everyone understand why I have these two equations? I have two temperatures, right? And the two different temperatures are going to give me two different diffusion coefficients. And that's what's going to give me the higher amount of carbon in my material. So we're trying to find out what T1 is and what T2 is. So I can move things around so that I can write this as LND0 equals and then you set these two equations to equal to each other. Because D0 is a constant, it's not going to change based on the temperature. And then now you can solve for T1 based on the answers that we got from the last time we went through it, and then solve for T2 based on the new information. So I'm not going to go over the details of that with you, but you can use the rest of today's class time to talk to each other if you need help, and you can ask me questions if you need help.